Hi, and welcome to our talk on frugal Byzantine computing. My name is Dalia, and this is a joint work with Marcos and Emma from VMware, Rashid and Thanasis from EPFL, and Igor from MIT. Now, as you see from the title, our work concerns Byzantine failures. And by that, I just mean that processes may behave in an arbitrary way, be it because of malicious intent or because of bugs. Let's see, what do we actually mean by this term frugality? And the first aspect of it is the number of replicas in the system. So you may know that to tolerate F-Byzantine replicas, one needs a system with 3F+1 participants to solve agreement problems. Now, we wondered, what if we use 2F+1 participants? And this would actually be much more convenient. That is because it would have 33 to 50% less hardware than a system with 3F+1 participants. And as you can imagine, this has a positive impact also on the costs. Now, a second aspect of frugality is the number of digital signatures. So digital signatures are super useful when dealing with Byzantine participants. And that is because they offer a nice property. So imagine a process signs a message. Now, this process later on cannot deny authorship for this event. Yet, unfortunately, signing a message is much more expensive. So it is about 28 times lower, as you see in this graph, as compared to just sending a message. So these two combined bring us to our goal, which is to address some of the traditional distributed computing problems, but by using 2F+1 processes and trying to minimize the number of digital signatures. Now, you may actually wonder, how do we want to use just 2F+1 processes instead of 3F+1 when there exists this lower bound? And the answer comes from literature. It tells us that using non-equivocation together with digital signatures, it allows us to keep the number of processes at 2F+1 for solving agreement problems. Now, the way we provide the non-equivocation capability is by using shared memory. So I'm going to guide you through one example in which you'll see that a process is prevented from equivocating, or rather, we can detect its equivocation if it happens. So consider three processes, out of which one is Byzantine, P0 in this case, and we let P0 just share a message M with all participants. It does so by writing M to its memory region. So this region is only writable by P0, but it can be read by all other processes. Now, P1 reads the message P0 wrote, and what it does, it just replicates it. It writes it to its own memory region. Because P0 is Byzantine, it will try to lie, to equivocate, and change its value from M to an M prime. Now we let P2 read the shared memory, which includes both the memory region of P0 and of P1, and then it will figure out that there's both M and M prime, and it doesn't really know what to believe. So there's one missing ingredient to actually link P0 with both these messages, and hence to let P2 detect that P0 is the one that equivocated, and that is this tool I was mentioning before of digital signatures. So we've already seen a little bit of our model. Actually, we use more than just the shared memory. We use the message and memory model, which allows us to also pass messages between processes. And we have access to single writer multi-reader atomic registers. And the way we construct this shared memory is by a collection of individual memories, which may only fail by crashing. For signatures, we allow each process access to two primitives, one to sign the message and the other one to verify whether a signature is valid. And as I mentioned, we use 2F+1 processes in the system, out of which F may be Byzantine. Yet, so that this problem does not become impossible to solve, these Byzantine processes are not allowed to write on a register that is not its own. So we do not break this single writer multi-reader capability. And we also do not let the Byzantine processes to forge the signature of correct processes, yet they may collude, they may collaborate with each other and, for instance, forge the signature of another Byzantine process by exchanging keys. So given this model, let's see what are our contributions So first, we looked at the problems of consistent and reliable broadcast, and we came up with algorithms to solve these two problems. And both these algorithms have a nice feature, which allows delivery of a message in a well-behaved execution without actually checking any signatures, nor even waiting for them to be created. We've also shown a separation in terms of the total number of signatures that need to be created by correct processes. So our lower bound results tell that we need one signature for solving consistent broadcast and O of n signatures for solving reliable broadcast. And from here, you can actually see that consistent broadcast is a much cheaper primitive as compared to reliable broadcast. Reason for which we decided to use this primitive in building a consensus protocol. So let's start first by introducing the problems of consistent and reliable broadcast, as well as algorithms for these problems. I'll start first by introducing process roles. Essentially, we separated the processes into multiple roles in the spirit of Paxos. So if you're familiar with this, this won't be strange. So we have one sender that invokes broadcast. Then we have the role of replicators, which are the processes that ensure that all the broadcast properties are satisfied. So these are like the working bees. What they will do is just replicate messages, for instance. And finally, we have the receivers, which are the processes that invoke deliver. Now, when I will refer to N and F, I'll refer to the replicators. So the sender may be correct or Byzantine, receivers similar, yet the bound F applies for the replicators. Also notice that if all processes have all these three roles, then this just becomes the standard model. Now, let's look at the problem of consistent broadcast. So the first property, validity, tells us that if the sender is correct and broadcasts message M, then every correct process eventually has to deliver this message. Consistency tells us that if two receivers are correct and deliver a message, then this message actually must be the same. And finally, integrity tells that if some correct receiver delivers M and the sender is correct, then it's got to be the case that the sender broadcasts this message. So let's actually see how do we satisfy all these three properties. And I'm going to introduce the algorithm by example. First, let's look at the fast path. And that is when all replicators are not Byzantine and are actively participating into the protocol. So when the sender broadcasts message M, what it would do, it would write M to its own register. Now the replicators would read this message and replicate it essentially. So they will just write it in their own register. When a receiver would like to deliver the message, it would scan the slots of the replicators. In this case, it sees unanimity, all 2f+1 replicators have the same value M, and this enables the receiver to just deliver M via the fast path. Now, this is all simple, but let's see what happens when one of the replicators is Byzantine. So outside of fast path, we actually have to ask the sender to append its own signature for the message. And once the sender writes both the message and the signature, the replicators would just read these values and write it in their own slots. Yet we notice here that the Byzantine replicator is just writing something random, an M prime and a signature for this message. Now notice, because the sender is correct, the Byzantine replicator cannot forge its signature. So sigma prime, it's not possible for it to be a valid signature by sender S for M prime. When the receiver scans the slots of the replicators, it would see M minus F, in this case, two signed values, M with a valid signature by the sender, as well as another signed message, M prime, which we can disregard because we know it does not come from the sender. Now, seeing these N minus F signed copies of M, receiver P may deliver M. Going to reliable broadcast, we see that it's quite similar to consistent broadcast, yet it has one additional property, totality. And this property tells that if some correct process, in this case P1, delivers M, then all other correct processes should be able to deliver a message as well. Now, if we combine this with consistency, we will actually get to agreement, and that is they will have to deliver the same message. So let's compare first how consistent broadcast and reliable broadcasts differ. You may realize that consistent and reliable broadcasts are actually behaving in the same manner when the sender is correct. So if you look at validity and the sender broadcasts some message, then all correct processes have to deliver this message. Yet what happens is that when the sender is faulty, consistent broadcast has very few guarantees. So some processes may deliver a message, other processes may not. But the difference is that reliable broadcast guarantees that as soon as one correct process delivers a message, all other correct processes should be able to deliver the same message. And you may already realize that our consistent broadcast algorithm will not be sufficient to ensure this additional property. So let's see why. Let's look at one example. So in this case, the sender is Byzantine and broadcasts message M. So initially it writes both M and the valid signature for this message in its slot. Now we let two replicators replicate both the message and the signature, and we let the receiver P0 scan all the slots of the replicators, find n-f, in this case, two signed values for validly signed values for M, and deliver this message. Now, because the broadcaster is Byzantine, it would just overwrite its value with M prime and a valid signature sigma prime for this message. We let the replicator R0 read and replicate this message, and we also let the Byzantine replicator just overwrite its slot with the new value written by the sender. Now, when the second receiver comes and scans these slots, it would find n-f validly signed messages for M prime, but it would also find another validly signed message M by the sender. And in this case, it does not really know what to deliver. It cannot deliver M prime because there is proof that the sender equivocated and there is another M. So it is possible that somebody delivered M before, which in this case P0 did. So delivering M prime is not safe, but the same story goes for M. Delivering M is not safe because it could as well have been the other way around and somebody could have delivered M prime before. So this is fine for consistent broadcast because it is allowed for P1 to not deliver something when the sender is Byzantine. But for reliable broadcast, one would need to actually ensure that P1 is also able to deliver what P0 delivered, in this case M. So to ensure this additional property, totality, we actually see that we need to do a little bit more effort. And this is also what our lower bounds results show as well. So while for consistent broadcast, we only need a single signature to be created to solve this problem, for reliable broadcast, our lower bounds results show that we need O of n such signatures. And if you'd like to take a look to how we constructed our lower bounds results, please check out our paper. So let's see how do we solve the reliable broadcast problem. And we use the init echo ready mechanism, which you may be familiar with. We also use the previous consistent broadcast primitive we have just constructed. And we also keep all the nice properties consistent broadcast has, which is the possibility of having a fast path. So when all replicators are correct and they are actively participating, we allow delivery of message when there is unanimity and there's no need to actually verify or wait for signatures to be created. While outside this common case, receiver is able to deliver as soon as it sees n-f valid proof sets for this message. Now let's introduce the reliable broadcast algorithm. First, we consider the fast path when all replicators are correct and timely. So when the sender broadcasts a message, it actually invokes consistent broadcast for this message. So now the replicators will need to deliver this message. And we already know that if two replicators deliver some message from the sender and the replicators are correct, by consistency, they have to deliver the same message. Once they deliver the message, the replicators would just copy over whatever message they delivered in their echo register. Now, a receiver can just read all the replicator slots, and if it finds unanimity, it is able to deliver via the fastpath. Now, recall that if one of the replicators is Byzantine or not actively participating, we allow a receiver to deliver as soon as there are n-f valid proof sets. I'm just going to show you here how to construct such a proof set, which we actually call a ready set. So let's assume that all replicators already wrote something in their echo slot. Now, what we have to ask them to do is to append their own signature for this value. And once they do that, they will go and read all the other replicator slots to see whether there is any other replicator that has the same value as itself, together with a valid signature from this replicator. So in this case, replicator R1 would find the value of replicator R2, which is validly signed by R2, and append it to the ready set. As soon as one ready set has n-f values, it is ready to be appended to the ready register. Now, if you'd like further details on our reliable broadcast protocol, please check out our paper. I think now we're ready to move on to our last point on the agenda, which is consensus. So once again, we use the cheaper primitive consistent broadcast to build the consensus protocol. Let's start by looking at the properties of consensus. So agreement says that if two correct processes decide on a value, then they actually must decide on the same value. We consider the problem of weak Byzantine agreement, which has the weak validity property. And this tells that if all processes are correct and some decides M, then M is the input of some process. Integrity tells that no correct process can decide twice. And finally, termination asks every correct process to eventually decide. Now, before we go and see how we ensure all these properties, let's check what features our protocol has. So it is actually the first broadcast-based protocol that works for two F+1 processes, out of which F can be Byzantine, and it issues no signatures in the common case within a view, respectively of and background signatures within a view, as well as of and square signatures and a view change. Now, this will become a lot clearer when we actually dive into the algorithm. So let's see that. It is based on the PBFT. If you're already familiar with, you know that replicas are proceeding in a succession of views, and each view has a primary. We use a consistent broadcast for communicating, and we also assume message ordering, so we ensure an additional property, which is FIFO. So let's look at one example to see how the protocol works. In this case, we have three processes, out of which one can be Byzantine. Let's assume P2 is the leader of the view. So it would try to impose its value by broadcasting a prepare message. Upon receiving such a prepare message, each replica would just broadcast back a commit message with the same value. Now, when one process receives n-f commit messages for the same value it has prepared, it is ready to decide. You can already see here that a process is able to decide after one invocation of consistent broadcast in the prepare phase, followed by n invocations of consistent broadcast for the commit phase, which gives us a total of n signatures within a view for reaching a decision. But this also allows us for reaching a decision without actually creating or verifying any signature at all. And recall, this is just the fast path of consistent broadcast when all replicators were non-Byzantine and actively participating in the protocol in a timely manner. Now, we also have to account for the case when the leader fails. And when this happens, we make use of the view change procedure. So each replica would broadcast a view change with its estimate that could have been decided upon. But the difference here is that replicas will have to reply back with an acknowledgement for the view change message if the view change message is valid. And we introduced this acknowledgement scheme for two reasons. So first of all, we would like to prevent Byzantine replicas from lying about their past, lying about the value that they might have decided within the view and they claim in the view change message. And secondly, recall that we use consistent broadcasts. So when the sender is faulty, we have very few guarantees with respect to correct replicas being able to deliver this message. So by having this view change proof, if you wish, we allow all correct processes be able to receive a view change message if it has a valid proof, as well as be able to enter the new view. And here you can also see where the O of n square signatures come from, and that is just the invocations to consistent broadcast. Now, perhaps this reminds you of reliable broadcast. So if within the view we use O of n signatures, and upon a view change, we have similar witnessing scheme, each consistent broadcast is actually acknowledged by n participants, then why not replace this witnessing mechanism by reliable broadcast calls? And if we do that, you may be surprised or not, we get an inconsistent result with respect to the properties of a consensus. I'll just quickly exemplify. So assume P2 calls reliable broadcast for a value M, and we let P0 decide this value. But in this case, say P0 is not part of the set of participants in the view change, and the value P0 decided is now lost. So once again, looking back at our broadcast, now we see that it does work for 2f+1 processes, out of which f can be Byzantine. We saw how we managed to decide without using any signature by the fast path of consistent broadcast, as well as using O of n signatures outside the common case and O of n square signatures on a view change. So to conclude, we have introduced algorithms for both consistent and reliable broadcasts, which have a super nice property of being signature-free in well-behaved executions. We have also shown this large separation between consistent broadcast and reliable broadcast in terms of the number of signatures required by correct processes. And given that consistent broadcast is a cheaper primitive, we have used it to build our consensus protocol. So I would like to conclude by saying that the message and memory model enabled us to use fewer participants, 2f+1 rather than 3f+1, for reaching agreement. And even though it was not possible to get rid of signatures altogether, we have managed to minimize these by just introducing this different behavior in the common case. So thank you.